The all-electric model's explanations of the nature of galaxies, stars, and comets are virtually devoid of gravity. The same is true at the level of the planets. In gravitational cosmology, planets are thought to form together with stars from a widely distributed gas and dust cloud. Why the minuscule grains should adhere to each other, and not turn each other into finer and finer dust through collisions, is only one of the unsolved problems of this model. With our realistic approach, we can imagine several possibilities of how planet formation could occur. We have already seen one possibility in the chapter on electric stars. It has been suggested that stars subjected to strong electrical stress eject part of their core in a nova explosion in order to increase the surface area and reduce the electrical stress. In this way, small companion stars, large gas planets, and possibly rocky planets like Earth could be born. Interesting speculations of this kind suggest that our solar system, with its varied landscape of small, rocky planets and gas giants, could be a somewhat unusual case by cosmic standards. The sheer number of very small planets and moons could indicate that there was at least one period of extreme electrical activity in our solar system's past, during which a brown dwarf star approached the present-day Sun and was split into the 4 present-day gas giants due to increasing electrical stress. In addition, all sorts of smaller rocky core fragments, the present-day moons of the gas planets, and possibly Venus, could have been formed. In gravitational cosmology, such behavior is hard to imagine. But the electric cosmos is much more dynamic, because electric and magnetic fields interact with each other, even over long distances. And the electromagnetic forces do not only have an attractive effect like gravity. They also repel so that collisions rarely, if ever, happen. Stars can communicate over vast distances through their electric fields and the electric currents flowing between them. Another way in which planets could form is provided by the Z-pinch effect. We have already seen that several plasmoids can form in a strong discharge. It can now be assumed that the Sun and all the planets formed in a single galactic lightning strike. A third possibility would be that our Earth is a former dwarf star, whose electric charge became so low compared to the surrounding galactic plasma that the glow discharge ended. The same could be true for all other spherical rocky planets and moons. They would all be former stars, older than the Sun, collected over time by today's Sun. When it comes to the origin of the planets, as in all other areas of plasma cosmology, there is still a lot of room for future research and new insights. We are only at the beginning of what may be the most exciting scientific voyage of discovery of all time. How planets are ultimately formed has yet to be clarified. But there is no doubt that the members of our planetary family have had a very turbulent electrical past. The surface features of the rocky planets speak for themselves. Mars has been explored in great detail in recent years. Therefore, we can look for clues on its battered surface. The red planet reveals a plethora of amazing features. This applies both to the shape of the geological structures and to their immense size. Among these extraordinary structures is the vast canyon system of the Valles Marineris, which stretches for 4,000 kilometers. The 3 huge, aligned elevations of the Tharsis region. The 26-kilometer-high Olympus Mons, whose steep slopes shoot up vertically for 4 kilometers. Extensive areas littered with rock fragments. Thousands of craters in various shapes. Strange geological structures whose origin seems mysterious. Since gravity is the only cosmic force the Standard Model recognizes, a host of rather dubious geological mechanisms had to be used, and misused, to explain the surface features of Mars. Water, wind, and glacial erosion, tectonics, and volcanism were employed. But even so, formations like these spherical domes, or these so-called spiders, remain inexplicable. Let's take a look at the Victoria crater, which is about 800 meters wide. It is said to be a typical impact crater, whose rim has been eroded by wind over millions of years, and in the middle of which strange dunes have been piled up. But an asteroid impact and Martian winds are wholly inadequate to explain its features. The biggest problem is the idea of impacts themselves. This applies not only to Mars, but to all the rocky bodies of the solar system. The vast majority of craters are circular, which speaks directly against asteroid impacts. That is because in the rarest of cases, impacts would occur at a 90-degree angle. Most asteroids approach at a shallow angle, so they should leave an elongated crater. Furthermore, one would have to expect a bowl-shaped excavated bottom. However, most craters have a very shallow floor. Central mountains and very sharp, stepped walls are also not to be expected from a simple impact. Of course, drawings and computer simulations can be manipulated in such a way that the desired appearance of a crater is achieved. However, such shenanigans do not have much in common with scientific rigor. Moreover, the standard impact models cannot account for other observed properties of craters. These include the smaller secondary craters, which are very often found right on the rim of larger ones. This image is typical of large craters. In every case, it is the small crater that was subsequently formed on the edge of the large one. We never see a small crater partially overlaid by a larger one. The inadequacy of the impact theory is particularly evident when looking at the numerous crater chains of the solar system. The probability of falling rocks forming such straight chains is practically zero. And even if it could happen, it doesn't explain why these craters, like those on Mars' moon Phobos, lie in grooves. In this lunar crater, we see not only a chain of craters, but also a prime example of a smaller, secondary crater on the rim of a larger one. In the electric model, large asteroids do not hit planets. Both asteroids and planets are charged bodies. The electrical stress to which an asteroid is subjected as it approaches a planet causes the large projectile to break apart or even explode when entering the atmosphere, as was the case with the meteorite over Tunguska in 1908. The electrical stress slowly eats away at the rock, until the remaining small fragments finally hit the surface. We have already seen such a breakup in comet Shoemaker-Levy 9. Only comparatively small fragments may hit the surface. Large asteroids do not reach the planet's surface intact, and do not create huge, circular craters. The popular catastrophic scenarios of devastating asteroid impacts are likely to be nothing more than pure fantasy. The Earth's electric field acts as a natural shield against such impacts. Older images of the space shuttle reveal the effectiveness of Earth's protective shield. Here we see space debris being catapulted back into space as it rapidly approaches Earth. Only the repulsive forces of electromagnetism can lead to these sudden changes in direction. The circular, shallow craters on rocky surfaces are evidence of the turbulent electrical past of our solar system. They could have been caused by powerful plasma discharges. At Victoria Crater, we can simulate the formation of such an electric crater. The surface of Mars apparently served as an anode, as a positive pole. It is known from laboratory experiments that dozens of small anode spots form on anode surfaces. They are the ends of the plasma filaments. The so-called dunes in the middle of Victoria Crater do not look like terrestrial dunes at all, because they are interconnected and have very sharp edges. Furthermore, it can be seen that their orientation is always towards the crater rim. It appears that these are hard, glass-like structures that were formed when the central plasma filaments moved outwards. Strong plasma discharges develop additional characteristics beyond the central strand of filaments. A secondary plasma layer is formed, at the foot of which more anode spots appear. Most of the current, which initially flows through the central strand, is shifted to the outer filaments as the discharge becomes stronger. Here you can see a laboratory image of such a plasma column. Around the central strand, a cylinder of additional filaments is formed. A schematic illuminates the three-dimensional structure. Within the resulting plasma cylinder, surface material is electrically sucked upwards, much like in a tornado. Ionized air molecules shoot to the site of discharge, creating strong winds. What takes place in a fraction of a second in the laboratory took several seconds on Mars. In the end, an electric crater was formed. Lightning often strikes multiple times in the same place, as the previously ionized plasma paths are used again. Small secondary craters, which lie at higher points such as the newly formed crater rim, are the result. Although Victoria Crater is, in many ways, a typical crater, its jagged rim differs from the mostly rounded rims of other craters. Apparently, there were instabilities during the lightning discharge. Here we see the well-known diachotron instability. The discharge, which is actually circular, initially forms a pentagonal or hexagonal shape. Further instability of the plasma leads to splitting into individual plasmoids. Craters that show signs of such instability are rather rare, but they do exist. Again, we can see that the secondary craters lie exactly on the rim of the larger crater. The hexagonal shape, which must remain a mystery in the asteroid impact model, points to the electrical formation of the craters. And as is always true in the fractal all-electric cosmos, what we see on one level also applies to other orders of magnitude. Here we see the galaxy M61 with its distinctly hexagonal shape. Diachotron instability on the galactic scale. A particularly puzzling observation in standard cosmology in recent years has been the hexagonal, rotating storm at Saturn's North Pole. But the explanation of plasma cosmology is simple. Again, we see an electrical discharge with a diachotron instability. Pyramid-shaped mountains on Mars also fall into this category. And here, the veil of a filamentary aurora shows signs of diachotron instabilities as well. The jagged structure is directly transferable to the jagged rim of Victoria Crater. Imagine how this electrical discharge reaches the ground as it gets stronger, and what kind of traces might be left at the end. The notion that the so-called dunes in the middle of many Martian craters were probably formed electrically is substantiated further by these images. The longer the central anode spots keep their initial location, the more surface material is melted into glassy, sometimes dome-like structures. The mysterious domes are just such solid, electrically hardened structures. We know exactly the same objects from terrestrial experiments, in which discharges were directed at an iron-rich surface. It is also known that lightning strikes can produce small, hardened spherules, which often have unusual surface features. The shape of craters ultimately depends on the material of the soil, the length and type of discharge, as well as possible instabilities. The stupendous lightning strike that formed Victoria Crater lasted only for a few seconds. But because plasma discharges are scalable, the same structures can be observed on a much larger scale over much longer periods of time. These images show the evolution of the supernova 1987A. This is the plasma discharge of a star, which takes place analogously to the formation of the Victoria crater and a plasma discharge in terrestrial laboratories. Initially, the center glows an electric light, but over time, it is the ring of anode spots that conducts most of the current. We are looking directly into the plasma column from below. When it comes to electrical discharges, it is important whether the affected area of the planet's surface acts as an anode or a cathode. When it forms the anode, the plasma discharge tends to linger in one place. The stronger the discharge, the longer it lasts, and the more rock is melted and electrically sucked upwards. The so-called dunes are the first step, the domes the second. If the discharge takes even longer, the initial craters will form elevations reminiscent of volcanoes. The individual filaments and cylindrical sheet currents of an electric discharge tend to arrange themselves at fairly constant distances from each other. This is the reason why crater rims are often terraced. It's also pretty much the only mechanism that can satisfactorily explain these terraced mountains on Mars. Long plasma discharges to a positive surface create electrical elevations. The largest known such elevation is Olympus Mons. The common notion that it is a shield volcano is in all likelihood incorrect. In the electric model, this mountain was pulled upwards within minutes in a gigantic electrical discharge. Its 4-kilometer-high vertical slopes mark the boundary of the outer plasma cylinder. Inside, the surface material was melted and pulled upwards by enormously strong electric forces. The secondary lightning strikes normally seen at the rim of the primary craters were naturally aimed at the summit here, as it is by far the highest point, 26 kilometers above the surrounding land. Several secondary impacts on the summit created stepped craters. The traces of the individual filaments move from one crater rim to the other. As can be seen in these laboratory images, extensive filamentary structures emerge near the central axis. If we take a closer look at the slopes of Olympus Mons, we can see a fine network of filaments. In this picture, we can see the gradual slope of the mountain. When a plasma discharge is particularly strong, several cylindrical sheet currents are formed, not just one. On this laboratory image, we can witness the increasing fanning out of sheet currents. It is the reason why particularly large craters often consist of several rings. Similar multi-ring structures can also be observed at stellar and galactic scales. The features of the plasma discharges remain the same, only the scales and time periods change. If a part of a planet's surface does not behave like a positive pole, but instead as a cathode, then the shape of electrical scars changes accordingly. At the moment of the lightning strike, electrons flow from a wide area to the point of impact. In the process, they heat the rock and carry it along. This results in structures that are conventionally misinterpreted as ejected material from a meteorite impact. We can see here that not all stripes converge centrally, as would be the case with a meteorite impact. Some stripes branch out outside the crater, just as is typical for discharge patterns. The stripes are also not elevated, but discolored regions. In the event of a cosmic lightning strike, the approaching electrons are drawn to higher elevations from where they launch into space. Around this point, material is electrically removed. What remains are central mountains. In the mainstream models, such central elevations are explained by a springback of the molten surface, similar to an object falling into a liquid. Apart from the fact that this only applies to 90-degree hits, it also does not explain craters like these. They have central elevations with a crater at the top. One might suspect a chance hit by a meteorite right at the top of the mountain, but since two craters with the same feature are right next to each other, such a coincidence is out of the question. However, repeated lightning strikes are not uncommon. The first large discharge is followed by a second, often weaker one, which takes the already ionized plasma path a second time and hits the same spot. Two parallel lightning strikes are also not uncommon. Due to the great mobility of the electrons, it is common for a longer discharge to the cathode to migrate across the surface and cut out material in the process. The crater chains are a direct consequence of this migratory behavior. Such a discharge to the cathode can take place in repeated impacts, leaving a series of craters. However, the impacts can also follow each other so quickly that the individual craters merge smoothly into each other. Long grooves are formed. Here you can see the transition from individual impacts to continuous grooves. This is the so-called footprint crater in a Martian region called Orcus Patera. This mixture of crater and groove is considered a mystery by astrophysicists who work with the asteroid impact model. We can see the very flat floor, which is typical of electric craters. Here, a powerful flash of lightning traveled across the Martian soil only briefly, but continuously. In this picture we can see a very similar event, with the difference that the discharge did not take place continuously, but with a short interruption to the current flow, possibly an electrical self-extinction. This image does not show a planetary surface, but a piece of steel that has been subjected to an electrical discharge in the laboratory. The flat grooves and distinct crater chains are identical to grooves and crater chains on Mars down to the finest detail. In this experiment with an aluminum-coated plastic ball, we can follow the formation of electrical grooves. Although most planetary surfaces are likely to have a fairly low conductivity in contrast to the aluminum coating, the structures are strikingly similar. Of course, this does not mean that the nature of the surface does not matter. It does affect the electrical craters and grooves. A smooth steel surface shows grooves and crater chains, while a coarse aluminum surface results in a disordered network of craters. When discharges to the cathode continuously cut material out of the surface, such conspicuous formations can occur. The flattened mountains are areas that have been largely spared from the discharges. But around them, huge amounts of surface material were electrically eroded in a very short time. An extremely strong discharge, in which part of the surface acted as an anode, probably created the elevations of the Tharsis region. Such violent discharges lead to a strong imbalance in the distribution of charges on the surface of the affected planet. It is therefore to be expected that a strong negative discharge will result at an adjacent location. And that's exactly what we're seeing on Mars. In addition to the positive elevations of the Tharsis region, there is the huge canyon system of the Valles Marineris. The many small grooves and crater chains that cover Mars pale in comparison to the size of this canyon, which would easily stretch from the North Cape to the southern tip of Italy. It is not uncommon for prolonged electrical discharges to increase in strength and then decrease again to the same extent. Individual filaments attract each other due to their magnetic fields, creating a single, giant plasma tornado. Here we see an example that was recently observed on the Sun. Here we can see the convergence of initial filaments on the back of a victim of a lightning strike. On Mars, the filaments cut a network of canyons into the landscape as they converged. As early as the 1970s, Ralph Jurgens noted with regard to the Valles Marineris,
"This entire region resembles nothing so much as an area zapped by a powerful electric arc advancing unsteadily across the surface, occasionally splitting in two, and now and then weakening, so that its traces narrow and even degrade into lines of disconnected craters."
Such particularly violent discharges usually take place in the form of so-called sigmoids. They have a distinct S-shape. Here we see a sigmoid on the Sun. This is a particularly strong variant of a sunspot. On other scales, too, we encounter this form of a very strong discharge again and again. Here is the sigmoid of the galaxy NGC 1313. And here's a sigmoid at the south pole of Venus. Such a sigmoid is characterized by the fact that one end is more positively charged and the other more negatively charged, as in the case of an unstable plasmoid that emits an electron and an ion beam. Now, when we return to Mars and the Valles Marineris, we see not only the shape of a sigmoid, but also a clear dichotomy in the surface features. The area in the north consists of lowlands and canyons that indicate a cathode surface, while the area in the south consists of mountains formed as positive elevations. A massive discharge, centered in this region, may have created this trench system. Here we see once again a sigmoid in the atmosphere of the Sun. If such a discharge reaches to the surface of a rocky planet, the result will be a huge trench system. There is hardly a picture that illustrates the electric nature of the Valles Marineris more clearly than this one. Everything that has been mentioned so far in connection with electrical discharges can be found here combined. Parallel grooves, crater chains, a shallow crater with a typical stepped rim, central elevations from which the electrons shot into space, laterally branching discharges in the form of Lichtenberg figures. Overall, very finely sculpted shapes that look like they were cut into the surface with a scalpel. This is very different from normal erosion processes. Here we can see a piece of steel that has been cut with a plasma torch. Compare the cut edge with the slopes of the canyon. The trenches of the Valles Marineris, which are up to 7 kilometers deep, were probably cut into the surface of Mars within a few minutes. Vast quantities of rock were sucked upwards in the process. This may be one reason why we are finding meteorites from Mars on Earth today. As the plasma discharge subsided, large amounts of uplifted rocks fell back down to Mars. They formed the extensive scree deserts, for which there is no satisfactory explanation in mainstream astrophysics. When there are huge electrical discharges on planets, one side may be more affected than the other. This is partly due to the approach of the charged object, which is responsible for the electrical stress. A pronounced dichotomy of planetary surfaces is therefore quite possible. Mars also offers a very good example here. The crust of the southern hemisphere is significantly thicker than that of the northern hemisphere. In addition, at first glance, there are many more craters in the southern hemisphere. This led astrophysicists to the erroneous view that the northern hemisphere must be younger. In standard cosmology, the age of planetary surfaces is often determined simply by counting craters. For obvious reasons, this simple method won't work if the all-electric model is correct. Within a few hours, a planet's surface can be covered with thousands of craters. The low-lying northern hemisphere of Mars, which at first glance appears free from electrical cratering, reveals a completely different picture on closer inspection. The vast plains are covered with an incredibly dense network of small craters that strongly resemble electrically treated metal surfaces. It looks as if several kilometers of the northern hemisphere were completely removed by a gigantic plasma tornado. The modern, high-resolution images of the surface of Mars convey very emphatically the violence with which electrical discharges cut very sharp scars into the surface. If life ever existed on the red planet, it was completely wiped out within a short period of time when another planet approached. Large parts of its surface, water, and atmosphere were sucked away. A rocky, red desert planet with a gaping wound remained.